Yeah, so I'm going to talk about learning structured implicit 3D shape representations. So our goal here is to have a 3D shape representation that can describe shapes accurately, concisely for any possible object, for any size of object, including a city and down to a molecule, and be able to evaluate efficiently. These are motherhood and apple pie for 3D shape representations. And in particular, I'm going to focus on tasks such as reconstruction from point samples or completion of a depth image. So you see part of the object, but not the whole thing, or analyzing the shapes. Great. Traditional representations could be called explicit representations, like, things like meshes and point clouds and voxels. They enumerate small geometric elements that together cover the entire surface of volume. And so they are very general. If you have enough of these shape elements, you can describe any shape, and they're scalable. If you have more shape elements, you can describe more complex stuff. But they're not generally so accurate. It just depends on well, they're certainly not both accurate and concise at the same time. If you have lots of little tiny shape elements, you can get quite accurate, but then you have a lot of shape elements, and so they're not concise. So an alternative to that, again, a traditional representation would be an implicit 3D surface, where instead of enumerating the elements of the surface, you instead define a function such that when the function has some value less than an iso level 0, let's say, then you're inside the object. And if you have the value 0 for this function, for points that are 0, you're on the surface, and for points that are greater than 0, you're outside. An example of such a function would be a sign distance function. But there's also, going back decades and decades and decades, there's a variety of different implicit shape representations that people have considered, polynomials or algebraics or things like that. And they have the advantage that they're accurate, but they're not always so general, and they don't have all the properties we want. So people have more recently considered using deep networks as the way to evaluate these functions. So if I have a latent code, maybe 128 values that describe my shape, and then I just learn how to decode that latent code along with an XYZ position, then I can compute this f of XYZ for the implicit shape. So I take in an XYZ to the decoder and another encode, and I output f of XYZ. And so again, if f of XYZ is 0, then you're on the surface, and if it's less than 0, you're inside, and so on and so forth. So this is just a different form for one of these implicit functions. And there's been a lot of work on this in the past, few years, couple years. The advantage for them with the early work is that the description of the shape is very concise. The latent codes are quite small relative to explicit representations. There's a lot of weights in the decoder, but those are generally shared across all shapes. So the per shape cost is quite low. But most methods for reconstructing a shape from a latent code and a learned decoder do not produce very accurate models. They often are learned for a single shape class, like just chairs, and they're not scalable, so you can't represent an entire city this way. And they're generally not very efficient. For every fxyz, you have to evaluate all the weights of a decoder network. But they have been successfully used for tasks such as 3D reconstruction and completion because they leverage a shape prior that's learned. So the latent code covers a shape space that isn't all possible shapes, and therefore can help fill in aspects of the shape that you didn't actually observe. Okay, so just as an aside, these implicit learned functions can be either trained with an encoder-decoder architecture like this, where the observation comes in and an encoder produces a latent code, and the encoder and decoder are trained together with, for auto encoding, can you reconstruct a set of shapes? Or they can be trained as a auto decoder, where for every example, you try to optimize a latent code such that it reconstructs your observation. And they're subtly different, but have, in particular, when it comes to completion, cases where you have a partial observation, the encoder can be difficult to train because it's only given partial inputs. And so, sorry, Zoom is popping windows up on me. And so usually auto decoders are preferable for completion applications. Okay, but in either case, methods that are purely implemented this way have many challenges. It's hard to imagine that you could have a single shape space with latent code with a small number of numbers such that it covers all possible shapes in the world, including like an entire room. And if you did, then you'd have a humongous decoder that would be very inefficient to evaluate. And you would only be able to cover shapes that are like the ones you saw during training. So I guess if you had an infinite training set and an infinitely large decoder or whatever, then this would work. But it's actually very difficult to think about covering a very large shape space with this kind of method. So in this talk, I'm going to focus on methods that are hybrids between explicit shape representations and implicit ones. So the general idea is going to be to use traditional computer graphics representations that explicitly decompose shape into regions or frequencies or things like that. And then for each of those components, we're going to store a latent code that's going to be interpreted by a deep network decoder to produce an implicit function. And then the sum of those, or the combination of those, is going to be our final f of xyz. That's going to be an implicit shape representation. So that's going to be the general approach we're going to use. This is a good idea because if we decompose space into smaller regions, then the shape space we have to learn is much easier. So if I took parts that kind of look like cylinders and flat areas and cubes and things like that, that's a much easier shape space to learn than all possible cities or all possible chairs or all possible objects. And so we can have a smaller shape space, and we can have a decoder that is not with millions and millions of neurons, but smaller, because the shape space that it has to encode and reproduce is much smaller. And we can do it more accurately because our encoders and decoder is handling smaller things. We can do it more scalably because we can compose as many of these explicit regions as we want, add more, and then we get a more complex shape. And we can be more general because we can describe arbitrarily large and complex shapes by composing smaller ones. So this is the general approach we're going to take and why I think it's a good idea. I'm not the only one to be investigating this. There are many, many, many papers with ideas related to this. We started doing this around CVPR 2020, as did others. And so I just don't want to make it sound like I'm the only person who's telling this story. But I am going to just describe 3 projects that we did in this space and kind of get into their details as representative examples. So I'm going to start with this approach called local implicit grids. It was done by Max Zhang, again at CVPR 2020. So the idea here is quite simple. It's decompose space into overlapping grid cells, store a latent code for each of those grid cells that describes the local shape within that grid cell, And then when you and have a shared decoder that decodes each of those latent codes into an f of xyz, and then do a blend of those across the 8 grid cells that cover any particular xyz in order to produce the final f of xyz to produce a final shape. So to implement that, there's a few things that we have to do. We have to first choose a grid size and think about that. And this kind of gets to why I think this is a good idea. If you chose your grid cells really small, then your shape space is almost trivial. Everything's, let's say, locally planar. You have differentiably sized grid cells, then everything's plane. And so that's not really very helpful. If your grid size is too large, then your shape space is too complicated. It's big enough to cover entire objects, and we're back to the problem: how do you have a latent code that describes all possible objects in the world? And so we try to pick a grid size that is at the part scale, like the reusable part scale. So you have parts of cylinders and parts of planar region, corners of rectangles and things like that. And we can do that because we live in the physical world where objects are designed at the scale of people, or at least the household objects that we've done experiments for. And so the fact that something is 10 centimeters large means something with regards to because of the size of people. And so we can kind of pick a grid size or a part scale that's kind of general across all objects, because it's in relation to the scale of how the world's designed for people. But anyway, so then once we have a grid size, we need to train a local decoder, encoder and decoder for the local shape space. And so we end up generating point samples from depth scans or from watertight surfaces by sampling points near the surface and training a network that can learn to predict f of xyz greater than 0 for the yellow points and less than 0 for the green points and 0 for the black points here on the surface. And we do that actually by training on a synthetic data set. We use ShapeNet to train our local decoder, even though we're going to use it for synthetic data sets. And the reason is that we would like our shape space to cover a wide variety of objects, and we would like the reconstructions to kind of follow the kinds of features that you would see in a synthetic data set rather than noisy ones that we would get from we don't really have ground truth for scanned objects, but anyway, it gives us the opportunity to get sharper reconstructions by trying to mimic the synthetic ones. Anyway, so then the last thing is to train the decoder. Here it's quite simple. We just use an ImNet, which is one of these decoders that I described before from 2019. It's a relatively small network that takes in a feature for each grid cell and then a point sample in coordinates that are relative to the grid cell, and outputs an f of xyz. And then given the 8 grid cells that overlap a particular point, we evaluate the 8 local implicit functions and sum them to produce the final value, or interpolate them, I should say. Okay, so that's a very simple thing. So the high level thing was we decompose space into a grid and we use local implicit functions rather than one big global. Just to give it a visualization of what the embeddings look like, and kind of gets at the point of the generality, which is that if we train on ShapeNet across multiple classes, then we get a shape space where patches from the grid decomposition cluster according to local shapes, not according to category. So this is getting at, we chose a size that's small enough that we're learning composable components, not class-based object such shapes. To get at that, we did an experiment to test the generalizability of this method, where we trained only on chairs. So we took ShapeNet chairs and trained only on those. And then we tested on objects of different categories. And These are reconstructions of shown